All right, welcome to today's Explainer, rookie. Grab your magnifying glass and your notebook because today we aren't just doing mathematics. No way. We are solving a crime. Welcome to the forensic lab of pure math, where numbers honestly don't always want to be found and equations will try their hardest to throw you off the scent. I'm going to be your lead detective today, and together we are going to crack open the secrets of quadratics. Now, you gotta wonder, how do you solve a math problem when the numbers are literally hiding in plain sight? In algebra, variables are basically just suspects wearing disguises. Our job isn't to just blindly guess who they are. It's to systematically strip away those disguises using logic, structure, and a few forensic techniques we like to call mathematical manipulation. Section 1. The Quadratic Mystery. Inspecting the crime scene. Okay, let's dive into this. Every good investigation starts right at the beginning, right? Let's put on our detective hats, duck under the yellow police tape, and check this out. Exhibit A. We have a highly suspicious equation. 5 over x plus 2 plus 3 over x minus 5 equals 1. This is our primary suspect, and right now it is super messy. It's totally full of fractions, denominators are clashing all over the place, and our target variable x is buried deep. If we just stare at it, the numbers are going to win. We need to force this equation to give up its secrets. Moving on to Section 2. Gathering the evidence. Standard operating procedure. Listen, no detective ever solved a case by panicking at a messy crime scene. We rely on a really structured step-by-step methodology to bring order to the chaos. So here is our tactical plan. Step 1, we eliminate the hiding places by multiplying both sides to clear out those pesky fractions. Step 2, we expand the brackets and collect our terms, basically lining up all our evidence in one neat little row. And Step 3, the masterstroke, a technique called completing the square, which is going to corner our suspect once and for all. Let's actually put this plan into action. Section 3, completing the square, the forensic lab. Now, what's really interesting about this slide is seeing how the chaos actually resolves. Step through these lab doors with me, rookie. We are going to process this evidence. At the top of our file, we've got our initial messy crime scene. For Step 1, to eliminate those hiding places, we just multiply both sides by the denominators, x plus 2 and x minus 5. And boom, just like that, the fractions are completely gone. We have a flat, linear string of terms. Then, for Step 2, we expand those brackets and pull absolutely everything to one side, collecting like terms. Watch as it perfectly resolves into a clean, quadratic equation, x squared minus 11x plus 9 equals 0. But we aren't done yet. For Step 3, we complete the square. We take that middle term, the minus 11x, and we literally just have it. That gives us x minus 11 over 2, all squared. We then subtract the square of that half number, which is 11 over 2 squared, and we keep our plus 9 parked at the end. We successfully isolated the x within a single bracket. The disguise is definitely slipping. Section 4. Cracking the code, the big reveal. So the crucial point is, we finally have our suspect cornered in the interrogation room. We've simplified it, we've completed the square, and now it is time to turn up the heat. By moving the constants to the right side and taking the square root, we finally fully isolate x. And look at what we get. X equals 1/2 times the quantity 11 plus or minus the square root of 85. We actually leave it in exact surd form, meaning we keep that square root perfectly intact to preserve the exact integrity of our evidence. The case of the messy fractions is officially closed. But hey, don't pack up your kit just yet. We've successfully cracked Exhibit A, but right as we close that file, a brand new one lands right on our desk, Exhibit B. This time, we don't even have to solve for x right away. Instead, we are tasked with a totally new mystery, forcing an existing equation to perfectly match a completely different format. A good detective doesn't rely on just one trick. Since completing the square isn't going to be our primary angle of attack for this specific formatting challenge, we need to introduce interrogation technique number 2, comparing coefficients. Honestly, this is basically like matching fingerprints at a crime scene. Let me show you exactly how it works. And this brilliantly illustrates our new suspect. We've got 4x squared plus 20x plus 5. We need it to look exactly like this identity equation, the quantity of ax plus b squared plus c. So how do we find the hidden constants a, b, and c? Well, we expand the brackets, which gives us a squared x squared plus 2abx plus b squared plus c. And now, we literally just match the fingerprints. Compare the x squared terms. The initial equation has a 4. The expanded identity has an a squared. So 4 equals a squared, meaning a absolutely must be 2 or negative 2. Next up, look at the x term. Our suspect has 20. The identity has 2ab. If we plug in a equals 2 into that, well, 20 equals 4b, meaning b equals 5. Finally, the constant term. The suspect gives us 5. The identity leaves us with b squared plus c. Since we know b is 5, b squared is 25, so 5 equals 25 plus c, which means c is negative 20. By just comparing the matching parts, we've completely cracked the identities of A, B, and C. Section 5, Real-World Stakes, Why This Matters. Now, I know what you might be thinking. Rookie. Okay, this is great whiteboard detective work, but why does it matter outside the lab? Who actually uses this stuff? Well, because these aren't just puzzles. They are essential survival tools out there in the real world. Doctors use these exact quadratic tracking models to calculate the critical time intervals when a drug's concentration in a patient's bloodstream is going up or down. Economists map out pricing strategies for massive corporations just by finding the peak of a quadratic curve. Scientists absolutely rely on these equations to calculate the rate at which an environmental disaster, like an oil slick, is expanding so they can contain it in time. And manufacturers? They use these models to minimize the precise amount of metal required to make canned goods, saving literally millions of dollars and tons of resources. When you learn how to manipulate equations, complete the square, and compare those coefficients, you aren't just moving abstract numbers around on a page. You are learning how to look at a really complex, messy reality, strip away all the noise, and uncover the hidden truths right beneath the surface. You've got the step-by-step tools, you have the analytical mindset, and for sure, you have the investigative rigor. So tell me, rookie, are you ready to crack your next mathematical case?